in general also depend on temperature. Also, how hot the flame is shows the color that will be displayed, and it is the color of flame that is used to distinguish the kinds of elements that are being exposed to that flame. Now, the process of the test. The test involves introducing a sample of the element or compound to hot, non-luminous flame and observing the color of the flame that results. Now, the flame has to be hot and it does not have to have a smoke or soot so that it will give a perfect result. The idea of the test is that sample atoms evaporate, and since they are hot, they emit light when being inflamed. Now, when you expose a sample of the elements in the flame, some of the atoms now from it, they evaporate. When they go up, they are exposed to that heat of the flame. They now give out a different light from the flame. Flame test is a relatively easy experiment to set up, and thus is often demonstrated or carried out in science classes in schools. You can carry out this test or this experiment even in the class because it's very simple. Samples are usually held in a platinum wire, cleaned repeatedly with hydrochloric acid to remove traces of previous analytes. Now, if you must have maybe a particular platinum wire have been used for several experiments. So you have to clean it with concentrated hydrochloric acid. So you remove samples of the previous element that was tested. And now hydrochloric acid is chosen because it's very volatile, as I said last time. It can evaporate rapidly. And a metal halide being volatile gives better result. Because the hydrochloric acid is volatile, it will help you to get a very good result. Different flames should be tried to avoid wrong data due to contaminated flames, or occasionally a variety of to verify the accuracy of the color. Now you test a particular element several times so as to be sure that the result is consistent. Sodium is a common component or contaminant in many compounds, and its spectrum tends to dominate over others. Now, sodium can easily contaminate most of the elements or compounds, and when you expose an element contaminated with sodium to flame, the color of sodium will overshadow that of the element. It becomes difficult for you to distinguish. So to test, the test flame is often viewed through cobalt blue glass to filter out the yellow of sodium and allow for easier viewing of other metals. Now, sodium gives very bright yellow color. Now, when you expose the flame through a cobalt blue glass, it will filter off all the yellow color. Then it will now expose the actual color of the element that is being tested. This is used to remove error caused by sodium contamination to most other elements or compounds. Now, results. The flame test is relatively quick and simple to perform and can be carried out with the basic equipment found in most chemistry laboratories. It's very easy. All you need is your platinum wire, the sample you want to test, concentrated hydrochloric acid, which you will use to prepare the paste and also to wipe off the surfaces of the platinum wire. And then you get a bouncing flame to produce very hot flame. That's all you need for the experiment. The test has difficulty detecting small concentrations of some elements, while too small a result may be produced for certain others, which tends to cause fainter color to not appear. Now, if the sample is very small, it will be difficult for you to detect its presence. And that is why the concentration of the sample must be very high when you are preparing the paste so that it will actually give you the result. Here is a picture of a student carrying out a test in the laboratory. Now you can see here we have a bouncing flame which is supplying very hot flame from a gas. Now, this is the platinum wire which is holding, and then the sample is attached at the tip of the wire and exposed to the flame. You can see it gives a particular color, which is something like greenish yellow with some part of yellow in it. Now, this is wearing glasses through which you could see clear, and then to avoid any cases of accident. So this is used now to carry out, this is an example. You can see you don't need anything, just a bouncing flame, and then the platinum wire, the bouncing flame, the platinum wire, the sample. You have here you have a beaker through which the sample is prepared, and maybe here is a container of the particular chemical or compound which is used for preparing the sample. Now we'll look at some examples of flame tests of some metals. Although the flame test only gives qualitative information, not quantitative data about the proportion of elements in the sample, quantitative data can be obtained by the related techniques of flame photometry or flame emission spectroscopy. Now, this test is not going to tell you the quantity of metal that you are testing. It won't give you the mass of metal, the amount of metal. It's only going to tell you that you have sodium. It is sodium that you are testing. You have sodium in that sample. You have magnesium, you have copper in that sample. That's all you need to know. That's qualitative results. But if you want to carry out a test that will give you quantitative result, that is the amount, the mass, the quantity, then you now use other equipment like photometry or flame emission spectroscopy. Now, some common elements and their corresponding colors. Let's see, aluminium. If you test for aluminium, expose it to flame, you will have silver white color in very high temperature, such as electric arc, light blue. You know, when the temperature is very high, like that of an electric arc that is used for welding over 2000 degrees Celsius temperature, it gives a light blue. But on a normal temperature, it gives a silver white. Then next is arsenic. Arsenic will give blue color when exposed to flame. Then boron. Boron will give bright green. Here we have in this picture showing tests for arsenic. Here is a platinum wire. The sample is inside here. This is the color exposed for arsenic. It gives blue. It gradually changes into full blue color. Then here also is for boron. This is a platinum wire. The sample is at the tip of the wire, and then you can see the color that was displayed. It's a bright green. Next, we'll see barium. Barium will give you pale and purple green. Pale and apple green, pale and apple green. Now it's either pale green mixed with apple green. Then beryllium will give white. Bismuth is going to give azure. Calcium will give brick red color, light green as seen through blue glass. If you view calcium through blue glass, you will get a light green. But if you view it physically, you are going to get a brick red for calcium. You can see two examples here in the picture. The first one is for barium. Barium, actually, this is a platinum wire through which the barium sample is exposed to flame. We are told that we'll have either pale and apple green. Here it is pale green because the greenish color is not very bright here. Pale is pale green. And then on this side is calcium. Calcium, this is a platinum wire. The sample is exposed at the tip of calcium. You can see it giving us a brick red color at the edges here. Brick red. This yellowish color, who knows, could be as a result of the presence of sodium sample in it. But at the edges, you can see the red color showing. Light green as seen through blue glass. But if you want to filter off the sodium, you now use that blue glass. If you do that, to filter of the sodium and you begin to get a light green. Next is cadmium. Cadmium will give you rick red, what is called rick red. Cesium will give yellow color. Then we have further examples and pictures that shows their test. Cobalt gives silver white. Silver white, this is it. Cobalt is exposed here, and you can see it's getting very shiny, gradually changing to silver. Chromium will give silver white also, the same color with cobalt. This is chromium carrying out, being tested. Then cesium will give blue violet. Blue violet. That means blue violet means it's going to be almost like purple. This is a cesium. Though it's not fully violet sort of, but it is bluish coming out through from the edges here. It's giving the blue color here at this stage. Then now we have copper 1. Copper 1 will give bluish green. Copper 2, non-halide. That's copper 2 that is not attached to any of the halogens. It will give green. You can see here, we have a clean display of copper 2 halide. The test is giving a very bright green color. Next here is copper 2, a halide. The copper 2 halide is attached to any of the halogens. We have a blue-green. It will give blue-green. Then germanium will give pale blue. Iron 2 will either give gold color when very hot, such as an electric arc. If a very hot flame like that of an electric arc is used for the test, or it will now give green, turning to orange. Hello, can you hear me? Hello? Okay. I hope you are getting me. Next is iron 3. Iron 3 will give orange brown. Orange brown. Now here we have in the picture a test that is conducted for iron 3. We give orange brown. Then next we have a hafnium. We display white color when tested on a flame. We have other tests here. Mercury we give red. Indium we give indigo and blue. Then potassium gives lilac flame. Lithium we give crimson red. Invisible through green glass. If you view the flame that is displayed when you expose lithium in a flame test through green glass, it will not show. Instead, you view it physically and you will see crimson red. Then magnesium, but it will not give any flame. But for forming metal, intense white, for burning metal, sorry, intense white, magnesium originally wouldn't give you any flame. But when you expose it to a burning metal, it will give intense white flame. Now, in the picture here, we have 2 examples of potassium being tested. It gives a lilac flame, very bright. Then we have lithium here. Lithium, we say, is crimson red. You can see displaying very a particular kind of red that looks like pink or sort of. It is referred to as crimson red. Next, test for magnesium. Magnesium 2. We have yellowish green. It will give yellowish green. In the picture here, sorry, manganese. You see manganese there. It gives greenish yellow. That is pale green, not perfectly green. Around this area, you could see it's somehow greenish yellow. Then molybdenum. Molybdenum, it gives yellowish green when exposed to flame. Sodium will give you intense yellow, invisible through cobalt blue glass. If you expose sodium through a cobalt blue glass, it will not show. That is why it is used to filter off sodium's, when sodium stains other elements. There is contamination of sodium other element, and you want to test that element that have sodium contaminant, you now expose it to cobalt blue glass. It will filter off the flame color of sodium, now enable you to detect and analyze the presence of the other element. Next is niobium. It gives a green or blue. Nickel will give you silver white, sometimes reported as colorless. In the picture here, we have few examples here, like manganese. Manganese, we say that it gives a yellowish green, greenish yellow, or pale green. Then intense yellow. Then we have nickel. Nickel, we've said, we give a silver white. You can see it's very bright here. Then we have manganese. Manganese, we say, will also give a yellowish green, which is the same color with molybdenum. At the base here, it is giving its yellowish green, which is pale green. Next, we have sodium. It gives intense yellow. You can see how bright it is, giving intense yellow. This is the platinum wire. The sample that is being tested is here, and the color display at its surface, you can see, is perfectly yellow. Next text is for phosphorus. Phosphorus will give you a pale blue green, pale blue, bluish green. Then lead. Lead will either give you blue and white. Then we have radium. Radium will produce crimson color when exposed to flame. Then rubidium will give red violet. Antimony will give pale green, and scandium will give orange. We have in the picture here some of the examples. We have rubidium. Rubidium we say we give red violet. You can see it's gradually turning to pink. Then we also have antimony. We said antimony will give blue, pale green. That is, in the picture here, it did not really show that greenish, but it is bright and is gradually will turn to green. Then in the picture, we also have lead. We say lead will be blue and white. Now, it is either blue sometimes, and sometimes it could be white. Here, it's blue. This is the sample, is a platinum wire, and you can see the color being displayed here is blue, even though this flame is also blue. Then next stage here, we have selenium. It gives what is known as azure. We have tin. Tin will give you blue-white. Strontium is either crimson to scarlet, yellowish through green glass, and violet through blue cobalt glass. You can get different color depending on the kind of color of the glass you use in viewing strontium when exposed to flame test. Now, when you are not viewing it with any color, you get crimson or scarlet, but it will give you yellow when you view through green glass. It will give you violet if you view through blue cobalt glass. For titanium, for tantalum, you get blue. For tellurium, you get pale green. Titanium will give you silver white. In the picture here, we have strontium. Strontium here, we say, will either give us crimson or scarlet. It will produce yellow when viewed through. In this place, it is viewed, not viewed through any color. Crimson can be a kind of bright, this is crimson yellow, bright, very bright yellow, which is when you are not viewing it through anything. It will be perfectly, it will now be yellowish if you view it through green glass. Okay, next we have thallium. Thallium is pale green. Vanadium will give you yellowish green color when exposed to flame test. Tungsten is green also. Then yttrium will give either carmine, crimson, or scarlet, any of these three. Zinc will give colorless, sometimes reported as bluish green. It's difficult to identify or to be able to see the color clearly, but that's why most times it is referred to as being colorless. But when it is intense, they call it bluish green. Then for zirconium, you get mild red. In the picture here, we have zinc. We said zinc will either give you color or bluish green. Zinc is being tested. The sample is inserted here, and you can see it shows bluish green here. Now, there are other elements like gold, silver, platinum, palladium, and a number of other elements do not produce a characteristic flame color. They don't show any color when exposed to flame tests, although some may produce sparks, as do metallic titanium and iron. Salt of beryllium and gold reportedly deposit pure metal on cooling. Most of these will not give color, but a very few will give some sparks, like metallic titanium and iron, while salt of beryllium and gold will deposit the metal when they cool. Now, next stage. Okay, any question about a flame test before we go to the next stage? Any question?
No.
Hello? Okay, now we go to naming of molecular compounds. Molecular compounds are named using a systematic approach of prefixes to indicate the number of each element present in the compound. Now, there are rules that you follow in naming molecular compounds. One, you remove the ending of the same element and add an IDE, just like in ionic compounds. When we start naming them, you will get to understand. When naming molecular compound, prefixes are used to indicate the number of a given element present in the compound. For instance, mono shows the presence of just one. Di shows that an element appeared twice. Tri shows it is 3 times, 3 molecules of the element or 3 atoms of the element. Then tetra shows 4, penta 5, hexa 6, and hepta 7, octa 8, nona 9, and then deca shows there are 10 of these elements present. If there is only one of the first element, you can drop the prefix. For example, CO stands for carbon monoxide, not monocarbon monoxide. Now we have just one carbon, one oxygen. So the mono there is saying oxygen is 1. So we have carbon, then monoxide. If there are 2 vowels in a row that sound the same, once the prefix is added, they conflict. The extra vowel on the end of the prefix is removed. For example, one oxygen will be mono. Now we have mono. Mono ended with an O. Oxide started with an O again. So we now have 2 O's. So in the naming process, we'll drop one of the O and take one. So it is now named as monooxide instead of monooxide, 2 oxygen as it is in this case, mono and oxide. So one of the oxygen will be dropped, one of the O will be dropped, sorry, and then we now have monooxide. The extra O is now dropped. Generally, the more electropositive atom is written first, followed by the more electronegative atom with an appropriate suffix. For example, in water, oxygen is more electronegative, while hydrogen is more electropositive. So hydrogen is written first before oxygen in water, and that's why it is H2O. Can be called dihydrogen monoxide. Going by the formula, we can call it dihydrogen monoxide. But although it is called water, organic molecules, as molecules made of carbon and hydrogen, along with other elements, do not follow this rule. When we discuss organic compounds, if we find something like that in our scheme, you see that the naming of organic compounds and the writing of the structure of organic compound do not follow this rule, that only electropositive more electropositive metals element comes first. Now, naming oxide, let's see, we'll start with oxide. An oxide is a chemical compound that contains at least one oxygen atom and one other element in its chemical formula. Oxide itself is a dianion of oxygen, O2 minus. Dianion means that it has two negative charge when it is in ionic form, oxygen atom. Metal oxide does contain an anion of oxygen in the oxidation state of 2. Now, its combining power now is 2, which is its valency. Its oxidation state is 2. If an element in group 1 is to combine with oxygen, you must have 2 atoms of that element. And that is why in the formula for water, we have H2O. Hydrogen is from group 1, and its combining power is 1. And the oxygen, which has an oxidation state of -2, we need 2 hydrogen atoms to neutralize it before a neutral compound is formed. So this is how, so if you have an element from group 3, you will need to balance the oxidation state of the 2 elements, the element with that of oxygen. Most of the earth crust consists of solid oxides, the result of the element being oxidized by the oxygen in the air or in water. You know, oxygen being quite reactive, even in the soil, most elements that are very, very reactive do not exist alone. They exist in combined forms with oxygen. And that is why when they are extracted, when they are mined, they have to be subjected to chemical means to extract them and purify them before they can be used. Even materials considered pure elements often develop an oxide coating. Some materials that are made of pure element, you expose them to air, they react with atmospheric oxygen, and they form a solid layer, which is the product of the reaction, which prevents them from further reacting. Such materials are resistant to corrosion. Example, zinc, aluminum, and that is why, you see, sorry, not zinc, but aluminum. You see, zinc will continue to react when it comes in contact with oxygen and moisture. It keeps on reacting, and the product of the reaction is an oxide. And that oxide of zinc continues to deplete. It gives a brownish, reddish brown color, which is known as rust. And that is why when you use zinc as roofing sheets, it keeps reacting, and before you know, it will rust, and then it start leaking. Now, scientists discovered that aluminum has this property that it reacts with atmospheric oxygen, and then it forms a layer which will cover off the surface of aluminum and will disallow it from reacting further. In that case, aluminum will now be free from continued reaction. It will now be that makes it resistant to corrosion. And that's why if you check most modern buildings, they are being roofed with aluminum roofing sheets. Aluminum is resistant to corrosion because of this property it has with oxygen. And then even materials considered pure elements often develop an oxide coating. For example, aluminum foils develops a thin skin of aluminum oxide called passivation layer. You see, now this is aluminum oxide. Aluminum belongs to group 3, and therefore it has an oxidation state of 3, +3. Now, oxygen, which has oxidation state of +2, -2, needs to be neutralized, to be balanced. So the only way to balance is to multiply the +3 with 2, which will give us 6, and also multiply the -3 with 3, which will also give us 6. That is why the formula for aluminum oxide is Al2O3, just as it is here. That protects the foil from further corrosion. So the formation of that oxide layer protects the material, the aluminum, from any corrosion or from further corrosion. And that is why you see building structures that are roofed with aluminum roofing sheet can last for many years, and yet there won't be any problem. Aluminum was able to solve the problem of corrosion of roofing sheet. You see, previously, they used asbestos. But scientists discovered that asbestos can easily dissolve into liquid layer and cause severe poisoning. Asbestos is highly poisonous to humans, affects the brain, cause a lot of things, slow down the development of children and so on, and also poison the blood. So now scientists decided that they have to replace asbestos from using them as roofing sheets, as well as using them as pipes for supplying water. So aluminium has now been very, very useful and recommended for roofing sheet because of this formation of oxide layer which prevents corrosion. Certain elements can form multiple oxide, differing in the amounts of elements combining with oxygen. Example are carbon. Carbon, we can have carbon 2 oxide, which is known as carbon monoxide. When you have just one oxygen, you can have carbon 4 oxide, which is carbon dioxide. The di there shows there are 2 oxygen atoms. And then we can also have maybe carbon 6 oxide and so on. But let's go on ahead, we'll see. Then we have iron. Iron can also form lower and higher oxide. We have nitrogen, which can still form up to about 3 oxide. Nitrogen monoxide, nitrogen dioxide, nitrogen, nitrogen. Yeah, we have nitrogen 1 oxide, which is dinitrogen oxide. It is known as laughing gas, a gas that is poisonous but can only stimulate the brain and makes whoever is exposed to it to begin to laugh uncontrollably. That's why they are called laughing gas. We also have, now you have nitrogen dioxide, you have nitrogen oxide. Silicon also have various oxides, titanium and aluminium. They both form lower and higher oxide because of the variable oxidation states displayed by this element. In such cases, the oxides are distinguished by specifying the number of atoms involved. As in carbon dioxide and carbon monoxide and carbon dioxide, or by specifying the elements oxidation number, as in iron 2 oxide and iron 3 oxide. These are ways that they use in distinguish. Now, these are examples of oxides that we have here. We have some oxide here. First, we have water, which can be known as a hydrogen oxide, or you can call it dihydrogen monoxide. Then we have nitrous oxide, which is dinitrogen monoxide, is the one they call the laughing gas. And then we also have nitrogen oxide, which can be referred to as nitrogen 2 oxide. When nitrogen display an oxidation state of 2, you have this. When it display, when it display, this is nitrogen dioxide, also known as nitrogen 4 oxide. When nitrogen is displaying oxidation state of 4, you have this. When nitrogen is displaying an oxidation state of 1, you have dinitrogen monoxide. Then here, when the oxidation state of nitrogen is 2, you have this. Then we also have dinitrogen trioxide. Here, dinitrogen trioxide, nitrogen has an oxidation state of 3. So you must times that plus 3 with 2 will give you 6. So that if you multiply minus 2 of oxygen with 3, you also get 6, and it forms a neutral compound. We have dinitrogen tetraoxide. Here, the oxidation state of nitrogen here is, if you multiply 2 by 4 for oxygen, it's going to give you 8. That means this must be multiplied by 4 again. 2 times 4 will also give 8, showing that the oxidation state of nitrogen here is 4. So, and then this compound is the same oxidation state with nitrogen in nitrogen dioxide, but it's only that the compound formed in this form. Then we have silicon dioxide. Silicon dioxide. In silicon dioxide, the oxidation state of silicon is 2, and that is why it is SO2. Okay, silicon dioxide is easily found in sand and also as quartz. We also have silicon monoxide. The oxidation state of silicon in silicon monoxide is 2. Then we have titanium now. Titanium dioxide. The IUPAC name is titanium 4 oxide. It is very useful in paint. It's a filler in paint. And then we also have titanium monoxide. It's a lower oxide of titanium. Then next we have a dititanium trioxide. Dititanium trioxide is a titanium with an oxidation state of 3. Titanium, it should be titanium 2 oxide. Titanium 3 oxide. The oxidation state of titanium here is 3. So if you multiply 3 by 2, it gives you 6. Just as if you multiply the oxygen oxidation state minus 2 with this 3 also gives 6, giving a neutral compound. Next is silicon. Silicon dioxide shows that the oxidation state of silicon here is 4. And that is why you have 2 atoms of oxygen, because the 2 we multiply the minus 2 for oxygen. Then we also have iron 2 oxide. Iron 2 oxide, meaning that the oxidation state of iron here is 2. We have iron 3 oxide, which you can call here, you can call this one iron monoxide, you can call this one diiron tetraoxide. The oxidation state of iron here is 3. And then next we have aluminum oxide. In aluminum oxide, the oxidation state of aluminum is 3. So to balance it up, you need 3 atoms of oxygen, which is the layer of aluminum that is formed to prevent further corrosion of aluminum. We have zinc oxide. The oxidation state of zinc here is 2. You can still call it zinc monoxide because it has got only 1 oxygen atom in it. It can be used for lotion as antibacterial and fungal properties. It has antibacterial properties, fungal properties, and also it can be used as food additives, white pigment. Now, any chemical substance that is used in food must be consumable chemicals. We have consumable and non-consumable chemicals. Most of the chemicals in the laboratory are non-consumable. If anyone consumes such, it can lead to death. So we have special chemicals that are referred to as consumable chemicals. Next is carbon dioxide. Carbon dioxide is common. Di there shows there are 2 atoms of oxygen, 1 atom of carbon. The carbon oxidation number here, oxidation state is +4 in this compound. We now have carbon monoxide or carbon 2 oxide. It shows that the oxidation state of carbon is 2, and that is why it is CO. It's a very poisonous gas that is part of the exhaust fumes of generating sets. When anyone is using a generator and put it in an enclosed environment in which he or she is inside, the person endangers his life because he's or her life, because carbon monoxide is one of the major components of the exhaust fumes from that generating set. When it is inhaled by human beings, it reacts when it diffuses from the air sacs in the lungs through the blood capillaries inside the blood. It reacts with the blood. Instead of forming what is known as oxygenated blood, that is blood mixed with oxygen, it will now form carbo-oxygenated blood mixed with carbon 2 oxide. When it goes, the blood now is supposed to transfer oxygen and deposit oxygen in the brain. Now, when it goes to the brain as carbo-oxygenated blood instead of oxygenated blood, there will be no oxygen to deposit in the brain. In such situation, the brain will now be lacking in oxygen. And if the brain lacks oxygen for some minutes, the person dies. And that is why people that are exposed to carbon monoxide, they die in cold blood without struggle. You must have heard in the news that people who slept with their generating set inside a flat whom all the rooms are locked were found dead in the next morning. It is because they continue to inhale carbon 2 oxide or carbon monoxide, which react with their blood and form carboxyhemoglobin, and therefore can no longer supply oxygen to the brain. And that makes them to die even in their sleep without a struggle. Next is calcium oxide. Calcium oxide, calcium has an oxidation state of 2, and that is why you have one atom of calcium and one atom of oxygen. Calcium oxide is, yes, calcium oxide is known as lime. It's known as calcium lime, and it's used in the manufacture of Portland cement. Last time I explained to you the processes involved in the manufacture of Portland cement. This calcium oxide is melted at around 1,400 degrees Celsius heat temperature inside an equipment known as rotary kiln. Now, the melted lime is now cooled rapidly at the exit from the kiln, where you have another equipment attached to it known as the cooler. The cooling section solidifies the melted calcium oxide rapidly and forms what is known as clinker. The clinker is now transported from the rotary kiln equipment through conveyor belt to another equipment, which is known as the crusher. The crusher now crushes the clinker, which are like stones, into smaller particles. The crushed clinker is now transported through conveyor belt again to another equipment known as the mill. The mill now will grind these particles into small powder. During the grinding process, there will be the addition of other chemical substances known as gypsum. The chemical formula is calcium tetrasulfate 6 dihydrate, CaSO4 plus 2H2O. Now, the function of the gypsum is to control the setting time of cement. Now, after this grinding and mixing with gypsum, it is bagged in the cement bag, and that is all about it. Now, that cement now, when you mix it with water, allow it to settle for some time, it hardens. The time from the period you mix it and when it hardens is known as setting time. That setting time is controlled by the amount of gypsum that was added, calcium tetrasulfate 6 dihydrate, during the process of milling the clinker. So this is one of the major applications of calcium oxide. It is also used to produce slake lime. Slake lime is calcium hydroxide. When you add water to calcium oxide, it gives calcium hydroxide, which is slake lime, and it's also an alkali. Next is, we'll now see, okay, before we go to naming of hydroxide, I don't know if you have any question from what we've discussed about oxide and their names. Any question?
I don't have a question.
Okay, let's look at hydroxide. Now, sodium hydroxide is the first one here. Sodium hydroxide is very common. It is called caustic soda. It is used for manufacture of soap, very common in the manufacture of soap. Any soap that you use, maybe bathing soap, you apply it on your skin and you start feeling itches. It's telling you that the quantity of sodium hydroxide that was added during the manufacturing process is higher than the normal quantity. And that is why you feel itches, because one of the major properties of sodium hydroxide is that it's corrosive, and it's corrosive, it can burn the skin. I remember briefly a student who, no, not one of our students who graduated and worked in Nigerian breweries, was in the section known as washing section. Nigerian Breweries is a company that produces alcoholic beverages as well as non-alcoholic beverages. Example, the Star and so on. These are the alcoholic. They have malt and non-alcoholic beverages. Now his job is the washing section is an area where the bottles that has been used will be reused again. So they need to be washed and sterilized so that it will not be pure, it will not harm people whenever drinks are put into them again. Now his job is to introduce caustic soda, solid caustic soda in a bag, pour it into the machine, whereby the machine will mix it with hot water, and then that hot caustic soda solution that is produced will now be pumped into the bottle, these beer bottles and malt bottles. When they pump it into it at high pressure, it will remove all particles, every kind of stain, destroy all kinds of bacteria that it might have contaminated. You know, when you look at used drink, already consumed drinks, empty crates, you see that sometimes you see cockroaches, you see all kinds of dirt in them. So when they go back to the company, they are subjected to this kind of treatment. Now, the job of this young man is to pour in caustic soda into the machine tank so that it will now mix with hot water and then transfer to the washing section and be pumped into bottles. Now, when he carried the caustic soda back, and there are protective clothing that are worn by staff, especially factory workers in factories. Now, that particular, he was on night duty. He wasn't on his protective clothing, which is what is his fault this time around. Now, when he carried the sample, the caustic soda back, he wanted to pour it into the machine. He slipped and it poured on him. Now, when he poured this caustic soda sample on him, you know, it's very, very corrosive. He was there alone struggling. Before my management and other people could come and discover that this guy is dying, they started looking for a way to process visa and take him abroad for medical treatment. Before they could finish the hurdles with visa, he died. So that is telling you that caustic soda is very, very corrosive. In case you handle it in the laboratory, you must be careful. You wear some gloves and then you know how to handle it so that it does not touch you. It's not only acid that is corrosive in the lab. Now we also have calcium hydroxide. The calcium hydroxide is also another good chemical that is also used in the manufacture of soap, liquid soap. You use calcium hydroxide to manufacture liquid soap. And then we also have potassium hydroxide. You use potassium hydroxide to manufacture liquid soap. I'm actually talking of potassium hydroxide. The hydroxide ion is a radical. A radical is a combination of one or two elements with a negative charge, negative or positive charge displayed at the top. That is a radical. Now, the hydroxide ion is a radical. It has a -1 oxidation state. That means if it is combining with elements in group 1 in the periodic table, whose oxidation numbers are +1, you only need one of those elements. And that's why here we have one atom of sodium, because sodium displays +1 and hydroxide displays -1. And also here, we also have one atom of potassium, because potassium displays +1 and the hydroxide is -1. But when we come to calcium hydroxide, calcium here belongs to group 2 in the periodic table. Therefore, its oxidation state is +2. It will need -2 to neutralize it. Now, since hydroxide ion has only -1, you will need let's say 2 moles of hydroxide ion. And that is why here we have OH2 combining with calcium. Then when we come to calcium hydroxide, it's also useful. It's used to manufacture cements. It can also be used in the manufacture of mortar and plaster. Next is aluminum hydroxide. Aluminum belongs to group 3, showing that its oxidation state that it will display is +3. Now, since aluminum displays oxidation state of +3, it will need -3 to neutralize it. Now, the hydroxide display only -1. So you will need 3 moles of hydroxide ion for you to be able to get a neutral compound with aluminum. And that's why we have aluminum hydroxide, AlO3. There we have beryllium hydroxide. Beryllium is in group 1, same thing as potassium and sodium. So that's why we just have BeOH. Cobalt 2 hydroxide. When in the name here, it is called cobalt 2. Cobalt 2 here means that the oxidation state of cobalt is 2. And because it is 2, you will need a 2 hydroxide ion. And that's why I have copper 2 hydroxide. Copper 2 hydroxide, same thing. Copper is a transition element.